today I'm going to report of some of the simpler lessons we learned by testing ERC-20 tokens using our evaluation framework named ERC-X. Do I have one? Thank you. Yeah. So let me start with the context of this presentation. So 1 year ago, we started the journey with developing ERC-X, and our mission is really to build a tool that allows to evaluate the quality of existing tokens and also developers to build better quality tokens. So we are trying to address the most used ERC standards, ranging from ERC-20 to ERC-1155. In developing our approach, we try to be rigorous in our examination of the standards and our coverage of the standards, and also we try to be complete in terms of bug finding tools. Yet, we want this tool to be easily accessible to any kind of persona, ranging from developers with technical background to auditors and even investors with less technical expertise. So about our test suites, we have released so far 2 public test suites, one for ERC-20, one for ERC-626 with 157 tests and 194 tests, respectively. And we have structured our test suite into different levels that corresponds to different levels of requirements with respect to the standards. So at the least level, you have the ABI test, which consists in syntactic checks and checks about modifiers of functions, up to the minimal and recommended, which represent obligations and recommendations from the standard. And we didn't stop that. We added more property tests using the expertise of our security auditors. We added security tests inside what we call desirable property tests. And finally, we have add-on and fingerprint. Add-on is for any property test that would use functions going beyond the standard, like batch transfer or transfer proxy. And fingerprint is simply for implementation choices, like is this standard using an infinite approval pattern, for instance. Let me mention that we have 2 upcoming test suites that will be released in November for ERC-721 and 1155. Right. So we try to compare our tool to existing tools for checking ERC-20 tokens. We compare to Open Zeppelin test suite and to Slither across different categories, such as what is the supported contract, what are the supported contracts, what interfaces are offered, what is the user friendliness, and what is the coverage of the tool. So I won't go into the details of that. We have released recently a blog post about it, and I'll let you look at that, but you can see on the figure that we are doing pretty well. So over the last year, we have tested our tool extensively, and we have collected a lot of ERC-20 tokens, more than 200K, that we used in continuously testing our test suite and our testing tool. And soon we realized that this data we had in our database could be useful to get a behavioral perspective on tokens. So going beyond the usual token economics and the statistics about the amount of money that is stored in tokens, we can now have a look that is more related to the behavior and the security of tokens. So we try to build tools for our auditors, but also for the community. So in the rest of this presentation, I will present some of the simple test and token analytics that we can build when having such a huge database of evaluations of tokens. So let's start with test analytics, and the first simple metric we can look at is the number of passing tests, and more specifically here, the distribution of these on some well-known list of tokens such as Etherscan and Uniswap. So if you look at this figure, you can see that for most of the tokens, they pass, let's say, between 19 and 95% of our test suite, while there are a few tokens that pass between 50 to 2/3 of the test suite. Trying to compare this further, we can display the density plot and put the 2 distributions on top of each other, confirming the common trend between those token lists and seeing a slightly higher passing rate on Uniswap because it is a smaller list with more curated tokens. Now, trying to understand these discrepancies between tokens, we can split down the previous distributions according to the level of the test. So here you have the split of those distributions according to the minimal, the recommended desirable test, and you have also the total number of tests. So what we can see here is twofold. The discrepancy are from the minimal and the desirable test, and this can be explained as follows. The minimal test, the tokens that do not satisfy the minimal test are usually the tokens that do not handle properly the zero amount. So for instance, BNB would revert on transferring a zero amount of tokens, whereas this is something that is prescribed by the standard. As for the desirable test, this is pretty normal. These are harder properties to satisfy, and thus less tokens satisfy them. Displaying the same distribution on Uniswap, we can actually confirm the previous observations, seeing, however, that it is less pronounced because of the higher satisfaction rate on Uniswap. Moving further and analyzing tests individually, we can see that they do not contribute to these results equally. So for instance, here you have the distribution of passing rates from our test suite, from a selection of tests from our test suite. And you can see at the top that there are some tests that pass on all tokens, such as the test involving the initialization of the user balance, or whether you can check the balance of any address, or that you cannot transfer more than your own balance. This is expected because this will be the first properties you would think of when implementing an ERC-20 tokens. At the bottom of that list, you can find tests such as the ones that are listed there, which involve the zero address. And indeed, this is something that is less taken into account by ERC-20 tokens. Displaying the same distribution on Uniswap, we can see that we have more tests that are passed everywhere. So the previous tests that were passing for every token are still satisfied, but we find more tests, such as the one handling the override of the approval mechanism. And at the bottom of this list, we still find the same test related to the zero address. So the previous metrics looked at tests individually, but now we can wonder what is the relationship between the tests. So here is a heat map displaying the covariance matrix between tests. And if you look at this heat map, we can make several observations. So this heat map first ranges from strong negative correlation with cool colors to strong positive correlations with warm colors. So first you can see that on this heat map you have only warm colors. So this is a good sign. It means that the tests in our test suite are all testing in the same direction. So in other way, you don't have conflicting requirements in the test suite. Second observation is that you can maybe see some white lines. These are due to the tests that are passing on all tokens, and so the correlation is not defined. Finally, you can see that there are some areas of stronger correlation. And if you zoom in on one of these, you can maybe, hopefully this is readable, these are tests that are related to the transfer of the zero amount. And this stems from the fact that those tests are actually testing kind of the same behavior, but are changing a few parameters. So here, these tests vary according to the source and the destination of the transfer. And this is due to the fact that we chose to be very fine-grained in our test suite in order to provide the best possible feedback to the user of our test suite. Displaying the same correlation heat map on Uniswap, we find the same patterns appearing, and we can confirm the previous conclusions. Now, moving on to the analytics on tokens, the simplest metric we can use to compare tokens is simply the number of passing tests. So counting the number of passing tests for tokens allows you to sort your list of tokens and, for instance, identify the list of top 3 and last 3 tokens. But counting the number of tokens is not really meaningful. You want to build something that allows you to identify the strengths and weaknesses of tokens. So we designed this multidimensional score by tagging each of our tests with a topic. So the topics include transfer, transfer from, balance, allowance, zero address, fees, etc. So we have categories, and we categorize each of our tests. So for instance, if you have a test that would check that when you want to use a transfer from, you need to check for the allowance, then we would tag this test as being belonging to the allowance and transfer from category. So using this multidimensional score, you can see that you can quickly see how tokens behave on each other. And on these top 10 tokens from ETScan, you can see the general good quality of tokens, but you are also able to identify the weaknesses of some of the tokens. Another advantage of this representation is that it allows you comparing tokens. So here is a comparison between BNB and USDC, and this way you can select the token that, if you're trying to mimic the behavior of some token, you will select the one that matches the category you want. So we also looked at the global behavior of the test suite. So we wanted to address and look at the popular belief that most of the ERC-20 tokens are duplicates of each other's. And we addressed this question from a behavioral perspective by computing what we call a fingerprint of a test. So the fingerprint of a test is simply the bit vector that is made of the evaluations of the test. And then we say that two tokens are twin of each other's if they share the same fingerprint. So in other words, they are behaviorally equivalent according to your test suite. So we looked at different metrics on ETScan and Uniswap, such as the number of unique fingerprints, the proportion of unique fingerprints, the average number of fingerprints per token, and what is the most frequent fingerprint. So for instance, here you can see that the most frequent fingerprint is the one where every test is passing, so confirming again the previous observations we made. But you can also see that there is quite a large number of twins on those list of tokens, ranging from 50% to almost a third of tokens. So we wanted to understand better how those twins tokens are behaving. So if you look at the two plots on the left, you can see the number of tokens according to the number of twins. And clearly what we can see here is that there are two packets. If you look at the histogram on the top left, you can see that those on the right are all duplicates of each other. So this is half of the distribution, half of the tokens on ETScan are really behaving the same. And the other half is really tokens that have twins to some extent, or a lesser number of twins. Now, if you want a more precise number, you can look at the density on the top right, or even if you want to estimate the number of twins per token, you can use the violin plot, which is on the bottom right. So being a twin or not is really like a yes-no thing. But we wanted to go beyond and trying to understand what is the distance, how much tokens are differing from each other. So this heat map displays some representation of the distance between tokens computed using the Hamming distance, because we are dealing with bit vectors. And you can clearly see that using the left-hand side graph, you can see the big picture. So this gives you the bird-eye view, showing clusters, and you can identify some tokens that are maybe standing out from this. Zooming on the right, you can see a more focused view, and you can start making observation. And for instance, here you can see that UIP and BAB are behaving the same, while they are very different from each other's. So this way you can start seeing how we can do some clustering between tokens and grouping tokens according to their behavior. And this is interesting because if two tokens are in the same cluster, then you can believe that they will behave in the same way. So if one token, for instance, has a vulnerability, then you can be suspicious about the other tokens that are on this cluster. Displaying the same heat map on Uniswap list, you can see that tokens are even closer to each other due to the higher satisfaction rate, and zooming in also you can confirm the previous observations. So getting to the conclusion, this is only the beginning. We are starting to test a lot of tokens, a lot of ERC standards. We have more advanced analysis. We will be releasing a blog post very soon. We have also classifiers trying to put tokens into classes. We are also designing some test prioritization mechanism in case you have a reduced time budget according to their bug finding capabilities. We are also running those kind of analytics on list of bad tokens, such as rug pulls and honeypots, in order to better understand their behavior and trying to get some sort of signatures for these tokens. As I said, we will address more standards. And finally, we are building APIs to not only provide the community access to our test suite, but also to these test analytics. And as a final word, I just want to mention that this is a small effort, part of a larger effort at runtime. We are building a lot of cool tools related to EVM semantics. So we have Symbolic, which is our symbolic debugger, which allows you to set breakpoints, inspect variables, and execute your program in a symbolic manner. You must attend Raoul's presentation tomorrow at 9:16. We have also Control, which is the symbolic version of ERCX and allows you to execute our test symbolically and will provide you with either a proof or a counterexample in case your test fails. And this is part of a larger tool, which is KVM, which is our formal semantics for EVM model in our framework K, which allows you to do symbolic execution and do formal verification using K claims. Thank you very much, and I'm looking forward to discussing with you.